Okay, ladies and gentlemen, let's go over what we did today. This is the class opener, and we did growth or decay functions here. We were supposed to look at each of these and decide whether it was a growth or decay function. In order to really understand this, what would be a good idea is to understand the notes. First thing is, how do we know when we have an exponential growth function? Well, we know algebraically that it has a b value that's greater than 1, but when you're looking at it visually, from left to right, the f of x will grow either to positive infinity or negative infinity, okay? So from left to right, it's right here, check this out. From left to right, it's going to go either to positive infinity or negative infinity. So it's either going up forever or down forever. So that's the key, to look at it from left to right, and it's either going to go from positive infinity, to positive infinity or to negative infinity. And that's the key. So if you take a look at this guy over here, let me actually draw it since it's not there. This one right here, that one goes to negative infinity. That's also a growth function. But let's not go for a growth function. Let's go for, man, could I make this any uglier? I guess I could. Let me try it. Let's say I had something like this. From left to right, what's happening? Is it growing? You might think it's growing because it's going up, but it's actually approaching the y value of 0, okay? So it's not approaching positive infinity or negative infinity. It's approaching a certain value, and that is the key to understanding an exponential decay function. That's what this says right here. From left to right, the function will decay, which means approach a certain y value, okay? So if it's approaching a certain y value, here's another one. If I have something way up here and it's just decaying, and now it's approaching 0 forever, then that's a decay function, right? What's the difference between the red decay function and the blue decay function? This is a regular decay function, and this is the one that's reflected over the x-axis. This one got reflected down here to this one. So if your a value was negative, it would be like this. If your a value is positive, your decay function's like that. Now, we haven't even talked about translations with h and k. But anyways, the first thing, the most important thing to understand is how to look at graphs when you're facing the question that we had right there in the class opener. And again, from left to right, if the f of x is growing either to positive infinity or negative infinity, like right here, it's going to positive infinity, that's a growth from left to right. Or growing in a negative infinity, towards negative infinity, that's a growth, but it's a negative growth, okay? When is it a decay? When you're from left to right, the function will decay, it approaches a certain value. So if it's going to positive infinity or negative infinity, it's a growth, but if it's actually approaching a certain value or approaching a certain value, it's a decay, okay? Let's go back to this guy. So this is obviously not going to positive infinity or negative infinity, which means that from left to right, it is approaching a certain value. And what is that certain value? You can see that that value right there is the y equals 2 line. So this right here is your asymptote, and that's the y equals 2. That's the asymptote right there. So this is definitely a decay function, okay? Let's move on. How about this guy? This guy, from left to right, is it growing to positive infinity or negative infinity? It's not going to positive or negative infinity. It's approaching a certain value, and that certain value is the asymptote 2. Okay, there it is, 2. Okay, so y equals 2 is the asymptote here also. And this is a decay function. So let's write down decay. What else could we say about this thing? Well, the original decay function always looks like this, approaching 0. But we could clearly see that this got shifted 2 units up. So the asymptote is y equals 2, right? We already said that. And you could also say that it has a k value of 2. And we could even go further and say what the a value, if we actually saw the function, would the a value be positive, which means that it did not get reflected, or would it be negative, which means that it did get reflected? Well, in this case, the a value would be positive. What else could we say about this blue graph that's a decay function that infinitely approaches the y value of 2? We could actually link last unit's notation of end behavior and use that or describe that end behavior right here with this blue graph. Let's do that. Let's talk about the end behavior of the blue graph. As x approaches positive infinity, that means as I'm looking at it in this direction, what is f of x approaching? Is it approaching positive infinity, negative infinity, or is it actually approaching a certain value? It's approaching the certain value y equals 2. So you would say down here, as x approaches positive infinity, f of x approaches, we're going to put positive 2. Now, you may be tempted to put y equals 2, but the truth is f of x is already y. That's what it is. F of x is really the y values, the outputs. So as you're going from left to right, as you're approaching positive infinity, the blue graph is infinitely approaching the f of x value of 2. So that's the notation for end behavior. Let's also do the notation looking at it towards the left. We always look at it towards from left to right, but let's look at it from right to left just to do the other part of this end behavior. So it's going to read this: as x approaches negative infinity, f of x approaches what? That would be positive infinity. If you're looking at it towards the left, where's it going? It's going to positive infinity. It's going to go up forever, right? It's going up forever. Okay. So these are all just important things that you should be able to do by looking at a graph, saying as much as possible, whether it's a growth or a decay function and all that other good stuff. Whoops. Looking at this one from left to right, does it grow to infinity? Yeah, it grows to negative infinity, so that's a growth, all right? That's a growth function. Of course, the a value is negative because it's going to a negative infinity. It's growing, it's a negative growth. What else could we say? The asymptote is right here at y equals 3, okay? You could say that your final function is going to have a k value of positive 3. All those good things. The notation for end behavior, let me write that down. So right here, as x approaches negative infinity, where's this graph going? It's staying right here. It's approaching what value? The value of y equals 3. So you could say f of x approaches positive 3. And let's do the other one, as x approaches positive infinity. This one says, as x approaches positive infinity, where's it going? It's going down. How far down? Forever. It's not really approaching a certain value. So as x approaches positive infinity, what's it doing? F of x is approaching negative infinity right there. So it's going down to negative infinity. Okay, I'm not going to jot down the rest of these. I'm just going to tell you the last one. Here's the last one. What could we say about this? Is this an exponential growth or a decay? Well, from left to right, does it go to positive infinity? Yes, it does. Or if it goes to negative infinity, it's also a growth. This is definitely a growth because it's going to positive infinity. What else could we say? The a value must be positive because the parent graph would open up on a growth function. From here, from the x-axis, it goes up. What else could we say? From the parent graph here, it got shifted a couple units down, so that means that the k is negative 2. K equals negative 2. The asymptote is y equals negative 2. The end behavior, as x approaches negative infinity, f of x approaches negative 2. As x approaches positive infinity, f of x is going to approach positive infinity because it's going up. I hope that makes sense. Be ready for that on the test Friday. Let's move on. On this part of the class, I just wanted you to write down this paragraph right here. Not so you could actually fill in the blanks, but to get you started on the right thought process when you look at a function, so you could start thinking about what the parent graph is, if it's an exponential growth or decay, if it actually gets reflected or vertically compressed or stretched, whether it gets translated h or k units up, down, left, or right. So this whole paragraph, I asked you to copy it down in class. If you're at home watching this for the first time, you should pause it, copy it down. That way you could look at these and go and try to fill these in so it could get you in the right thought process when you're trying to analyze these functions. So let me just jump right into it. I'm actually going to, hopefully you guys already copied it down. If not, pause it and do it. I want to get rid of this top paragraph. I'm just going to move it out of the way because I already know what to think here. Let's look at this one right here and let's go through it. What could we say about this? The parent graph is y equals 1/2 to the x power. Notice I ignored the a value. I just jumped to the base and the exponent x. I ignored h and k also. So what else could we say about this? Well, what is the a value? The a value is 3/2. Now, what does that a value actually tell us? The a value is 3/2. Is the a value greater than 1 or less than 1? It's greater than 1. It's actually 1.5. So that does cause a vertical stretch with the factor of 3/2. So I guess the best way to say it is that the parent graph y equals 1/2 to the x power gets vertically stretched by that a value 3/2. And it also has a translation. Translated 4 to the right and 2 units down. How did I get 4 to the right? You have to think h, which is opposite of -4. So the h value is really positive 4, which means 4 to the right. The k value is -2, which means that you take it for what it is, which means it's going down 2 units. So that gives you your translations of 4 to the right and 2 units down. And all of this stuff that we're saying right here, guys, is giving us an exact transformation from the original y equals 1/2 to the x to the new entire function, right? So we could even start drawing all the descriptions of these things, right? What does let me just do a quick xy plane here. What does the decaying function y equals 1/2 to the x look like? Well, the parent graph looks like this, right? And then, does it get reflected? Well, does it get reflected? It depends if your a value is negative. So in this case, it does not get reflected. But it does get stretched. How do I know it's stretched? Because the a value is greater than 1. If it were less than 1, it would get compressed. So what does stretched mean when it comes to this blue graph? Stretched means that it gets a little bit more narrower, right? It gets a little bit more steeper, okay? And if it were compressed, a vertical compression makes it a little bit closer to the x-axis, so it's a little wider. So because this is greater than 1, it gets a little stretched. So let me do that in the red color, a little stretched, same end behavior, just got a little bit stretched up, vertically stretched. And let's talk about the translations, 4 to the right and 2 down. So I need to take this guy and move this guy 4 this way and 2 down. So let me do it moving it 4 that way and then 2 down. You're going to have a new asymptote down here. So here's your final graph, this black one right here. Okay. So you went through all the transformations, and now you really have a true understanding of how it gets transformed from your original blue one to the vertically stretched one to the translated 4 to the right and 2 down, which gives you your black one. If you were to graph this big one, this entire function on a graphing calculator, you would see that it really does look like this black one right here. And we could deduce all of that without using a graphing calculator, just understanding all the parts of exponential functions.